Right now, there are only two ways to cross a deep body of water. You either go over it with a bridge, or you dig under it through solid rock. Both methods have hard limits that engineers have been crashing into for over a century. And here is a number that puts the problem in perspective. The deepest underwater tunnel ever built sits about 290 meters below sea level, but some of the water crossings the world desperately needs are over 1,300 meters deep. That means the best tunneling technology on Earth can only reach about 1/5 of the way down. For decades, the answer to that gap was simple. We just did not cross those waters. Entire coastlines remained cut off from the mainland. Islands stayed isolated. Economies that should have been connected stayed apart. Engineers kept looking at the same two options, bridge or tunnel, and kept hitting the same wall. But in July 2025, a team of researchers at Tsinghua University in Beijing, working alongside engineers from Imperial College London and the China Academy of Railway Sciences, published a paper in the journal Nature Communications that quietly proposed something the engineering world had been chasing for over 100 years. They designed a tunnel that does not sit on the ocean floor. It does not get drilled through bedrock, it floats. Suspended in the water itself, held in place by its own buoyancy and anchored by cables to the seabed below, a structure that ignores the depth of the ocean floor entirely because it never touches it. There's actually a much bigger story behind all of this that I couldn't fit into this video. So I put it together in an ebook for anyone who wants to go deeper. You can find it in the description or scan the QR code on screen. Now let's get back to the video. The reason this matters goes far beyond one research paper. To understand why engineers around the world are paying attention, you need to know why crossing deep water has been one of the hardest problems in civil engineering, why every method we have used so far has a breaking point, and what makes this floating tunnel concept so different from anything that has been tried before. The two methods that built the modern world. Think about the last time you drove through a tunnel under a river or flew over a bridge spanning open water. Those crossings feel routine. You barely think about them, but every single one of them exists because engineers solved an incredibly difficult problem using one of just two approaches. And both of those approaches have limits that most people never hear about. The first method is the bored tunnel. This is how the Channel Tunnel between England and France was built. Giant tunnel boring machines, some as long as a football field, grind through solid rock beneath the seabed. The Channel Tunnel runs about 75 meters below sea level at its deepest point. It took 6 years, cost the equivalent of over $22 billion in today's money, and required boring through a specific layer of chalk marl that was stable enough to hold a tunnel. If that layer of chalk had not been there, the tunnel might never have been built at all. The second method is the immersed tube tunnel. Engineers prefabricate massive concrete tube sections in a dry dock, float them out to the crossing site, sink them into a trench dug along the seafloor, and then connect them end-to-end underwater. This is how the Dalian Bay Undersea Tunnel in China was built, a project that won Global Project of the Year in 2024. It works extremely well, but only when the water is shallow enough to dig a trench along the bottom and the seabed is stable enough to hold the weight of a concrete tube. Most immersed tunnels sit in water that is between 5 and 30 meters deep. Once you get past about 100 meters, the technique hits its practical ceiling. Both methods share the same fundamental assumption. The tunnel has to either sit inside the ground beneath the water or rest on the ground at the bottom. The ground is the foundation. Without it, you have nothing. And that is exactly why certain crossings have defeated every engineering plan thrown at them for decades. The ground is either too deep to reach, too unstable to build on, or the geology is so hostile that no boring machine on Earth could cut through it safely. If the water crossing you need sits above a seabed that is 500 meters down, or 1,000 meters, or 1,300 meters, then a bored tunnel is not an option. The pressures are too extreme, the rock is too unpredictable, the cost would be almost infinite. And an immersed tube is out of the question because you cannot dig a trench in the deep ocean floor and expect it to hold. A bridge might seem like the obvious alternative, but bridges have their own breaking points. The longest main span of any suspension bridge on the planet right now is a little over 2,000 meters. Some of the crossings that need to happen stretch across 3,700 meters of open water with nothing in between to anchor a support tower. And even if you could stretch a bridge that far, the towers holding it up would need to be taller than the Eiffel Tower. Nobody has ever built anything like that over open ocean. So the world has been stuck. not because we lack the ambition to connect these places, but because the physics of bridges and traditional tunnels have actual limits, and those limits have turned certain crossings into engineering dead ends. Understanding why those dead ends exist is what makes the next piece of this story so remarkable. The crossing that broke every plan. No place on Earth illustrates this problem better than the western coast of Norway. Highway E39 runs 1,100 kilometers along one of the most beautiful coastlines in the world, from Kristiansand in the south to Trondheim in the north. But the drive takes 21 hours because the road is interrupted by 7 fjords. At each one, drivers have to stop, load their cars onto a ferry, wait, cross the water, and then continue driving on the other side. Norway has been trying to eliminate those ferry crossings for years. Some of the fjords can be handled with traditional solutions, but one crossing has stopped every plan dead in its tracks, the Sognefjord. It is Norway's longest and deepest fjord. At the point where the road needs to cross, it is 3,700 meters wide and 1,300 meters deep. Let those numbers sink in for a moment. The water is deep enough to swallow 3 Eiffel Towers stacked on top of each other, with room to spare. Building a bridge across it would require a suspension span nearly twice as long as any that currently exists, supported by towers 450 meters tall, planted on the ocean floor 1,300 meters down. That is not just difficult. It is, with current technology, essentially impossible. A bored tunnel beneath the seabed is no better. The geology beneath the Sognefjord includes hard bedrock at extreme depths. Drilling a tunnel path that would go down far enough to pass beneath the fjord floor and then come back up on the other side would create a tunnel so deep and so long that the engineering challenges would multiply beyond any reasonable budget, and the seabed itself is too deep for an immersed tube. Norway allocated $40 billion to upgrade the entire E39 highway. They have been working on it for years. They have built some of the world's most impressive underwater road tunnels as part of the project. But the Sognefjord remains unsolved, and Norway is not alone. China faces the exact same kind of problem with the Qiongzhou Strait, the 30-kilometer wide body of water that separates Hainan Island from mainland China. The strait sits in a seismically active zone with frequent typhoons, strong currents, thick marine sediment, and underwater volcanic features. Engineers have studied that crossing for over 20 years. Plans have come and gone. Feasibility reports have been written and shelved. The chief engineer of the Hong Kong-Zhuhai-Macau Bridge, one of the most complex marine engineering projects ever completed, publicly stated that the Qiongzhou Strait poses even greater challenges than the bridge he built. China also has the Bohai Strait, a proposed 125-kilometer crossing that would connect the economic powerhouses of northeast and eastern China. That project alone carries an estimated budget of $43 billion and would need to run about 90 kilometers beneath open sea. Both crossings remain in the planning stage because the traditional methods simply cannot handle them. These are not hypothetical problems. These are real crossings that real economies need. And every approach that has been tried has hit the same wall. The water is too deep, the ground is too hostile, the spans are too wide, the costs are too extreme. That wall is exactly what the team at Tsinghua University decided to break through. And the way they did it is something engineers have been theorizing about for over a century, but nobody had ever figured out how to actually make work. The tunnel that does not touch the bottom. The idea behind a submerged floating tunnel is simple enough to explain in one sentence. Instead of putting a tunnel in the ground beneath the water, you float it inside the water itself. Picture a massive concrete and steel tube, big enough for 6 lanes of traffic, suspended about 20 to 50 meters below the surface of the water. It is deep enough that the largest ships in the world can pass safely over it without any risk of collision. It is shallow enough that the water pressure is manageable, nothing close to the crushing forces at the ocean floor. And it is held in position by a combination of 2 forces. Its own buoyancy, because the structure is designed to be slightly lighter than the volume of water it displaces, pushes it upward, and tether cables anchored to the seabed pull it downward just enough to keep it locked at exactly the right depth. Think of it like a submarine that never moves. It just sits there, floating in the water column, anchored by cables the same way a hot air balloon is held by ropes tied to the ground. The depth of the seabed beneath it does not matter at all. The tunnel could float above water that is 100 meters deep, or 1,300 meters deep, or 5,000 meters deep. All that changes is the length of the cables. The tunnel itself stays in the same comfortable zone near the surface. This single shift in thinking eliminates the biggest constraint that has blocked deep water crossings for a century. The depth problem simply disappears. The concept has been around since the early 1900s. Engineers in Norway, Italy, Japan, and China have all studied it on paper. The idea even has a poetic alternate name. It is sometimes called an Archimedes Bridge, after the ancient Greek scientist who discovered the laws of buoyancy. But for over 100 years, the concept stayed on paper because nobody could solve the engineering challenges that came with it. A tunnel sitting inside the ocean is not like a tunnel buried in solid rock. Solid rock does not move. Water moves constantly. Currents push against the tunnel from the side. Waves from the surface create vibrations that travel down through the water and shake the structure. Over years and decades, those vibrations create something called fatigue, tiny cracks that grow over time until the structure fails. If a fire breaks out inside the tunnel, there is nowhere for the heat to go. In a regular tunnel buried in rock, the rock absorbs some of the heat and provides structural support even if the concrete weakens. In a floating tunnel surrounded by water, a fire that weakens the tunnel wall could cause a breach. Water floods in, the whole structure could catastrophically fail. These are not small problems. They are the reason no submerged floating tunnel has ever been built anywhere in the world. Not in Norway, not in Italy, not in Japan, not anywhere. The concept has been theoretically attractive for a century, but every time engineers got serious about building one, they could not figure out how to make the structure survive the combination of ocean currents, wave vibrations, fire risks, and the sheer duration of a 100-year service life, all while keeping the cost reasonable. That is the wall the Tsinghua team broke through, and they did it by completely rethinking what the tunnel itself is made of. The design that changed the math. Previous submerged, floating tunnel designs almost always used a single large tube, one big hollow cylinder made of either steel or reinforced concrete, wide enough to carry traffic inside it. When engineers tried to make that single tube strong enough to resist ocean currents, the walls had to get thicker. When the walls got thicker, the structure got heavier. When it got heavier, it needed more buoyancy control and bigger cables. Every improvement in one area made another area worse. It was an engineering trap. The Tsinghua team, led by researcher Fa Cheng Wang, took a completely different approach. Instead of one big tube, they designed a system of 3 smaller tubes arranged in a triangular truss formation and connected by a lattice of steel braces. Each of the 3 tubes is made from a hybrid material, 2 layers of steel with concrete sandwiched between them. The technical name is concrete-filled double-skin tubular structure, but the concept is straightforward. Think of it like a thermos bottle. An outer steel wall, then a layer of concrete, then an inner steel wall. The traffic rides through the inside of the tubes. The concrete in between does multiple jobs at once. The outer steel wall gives the structure its shape and resists the immediate force of ocean currents. The sandwiched concrete supports the outer steel wall from the inside, preventing it from buckling. It also acts as a heat shield. If a fire breaks out inside the tunnel, the concrete absorbs and blocks heat from reaching the outer wall, keeping the main structural steel at a safe temperature far longer than a steel-only tube would survive. The inner steel wall holds the concrete in place and prevents it from cracking or spalling during an explosion or impact. And here is where the truss formation matters. By arranging 3 tubes in a triangle and connecting them with steel braces, the structure becomes massively stiffer than a single tube of the same weight. It is the same principle you see in construction cranes and bridge trusses. A triangle distributes forces more efficiently than a cylinder. You get more strength per kilogram of material. The team tested their design against 3 conventional approaches using advanced computer simulations validated against real laboratory experiments. They published every test result, every number, every step of their analysis in the Nature Communications paper. They did not ask anyone to just trust them. They showed the math and let the world check it. The numbers that silenced the skeptics. When the Tsinghua team compared their triple-cord design against a conventional single steel tube of the same cost, the results were not even close. Under lateral ocean current loading, the new design reduced maximum sideways displacement by 60% compared to a single steel tube. That is not a small improvement. That is the difference between a structure that bends dangerously far out of position and one that barely moves. The conventional single-tube designs actually exceeded the safe displacement limit set by Chinese engineering codes. The new design stayed well within it. Structural stiffness, which measures how well the tunnel resists bending, improved by 400% over the single steel tube. Even compared to a single tube filled with concrete, the improvement was 200%. Compared to a steel-only truss without the concrete sandwich, it was still 35% stronger. The fatigue numbers were just as striking. The concrete sandwiched between the steel layers reduces stress concentrations at the joints where the braces connect to the main tubes. That is exactly where fatigue cracks start. By cushioning those joints with concrete, the team increased fatigue life by approximately 94%. In practical terms, the conventional steel-only truss failed to meet the 100-year service life requirement under the same loading. The new design passed it. Then came the fire test. In a simulation of 1.5 hours of internal fire exposure, the temperature in the steel-only tube rose dangerously across its entire wall thickness. The steel would have weakened to the point of structural failure without expensive fireproof coatings. In the new design, the concrete layer absorbed the heat so effectively that the outer steel tube, the part doing most of the structural work, barely heated up at all. The fire could burn for an hour and a half inside the tunnel, and the structure holding back the ocean would remain essentially undamaged. All of these improvements came at the same material cost as the conventional designs. The team designed every comparison so that the total amount of steel and concrete used was the same across all four approaches. The new design does not win by using more material. It wins by using the same material in a smarter way. Why this one is different from everything before it. Many promising engineering concepts look good in simulations, but fall apart when you try to actually build them. So the natural question is, can this really be built? The answer comes down to something the paper addresses directly. Every component in the design, concrete-filled steel tubes, hollow steel braces, truss connections, uses construction techniques that are already mature and widely used in real projects. Concrete-filled steel tubular structures have been used in building columns, bridge supports, and offshore platforms for decades. Truss structures are one of the oldest and most reliable forms of engineering. The innovation is not in the individual parts. It is in how they are combined and applied to a floating tunnel. The design is also highly adaptable. The team ran a sensitivity analysis on 13 different design parameters, testing how changes to each one affected both performance and cost. They found that adjusting just 3 parameters, tunnel length, section height, and the distance between tubes, could control displacement without significantly increasing cost. That means engineers designing real crossings could tune the structure to match local conditions without starting from scratch. And there is one more advantage that separates this from previous submerged floating tunnel proposals. The cost structure scales differently than traditional tunnels. With a bored tunnel, cost per kilometer increases as the crossing gets longer because you are fighting geology the entire way. With an immersed tube, costs increase with depth because the trench and placement operations become exponentially harder. A submerged floating tunnel has relatively stable cost per kilometer regardless of depth and distance. The tunnel itself does not care how deep the water is beneath it. That means the crossings that are most expensive and most difficult for traditional methods are actually the ones where a floating tunnel has the biggest advantage, the race that has already started. China has been preparing for this kind of technology for years. The China Communications Construction Company commissioned a joint research project with TU Delft in the Netherlands and the Tian Research Institute to specifically study submerged floating tunnels for Chinese waters. That project covered 11 areas of research, including design, construction methods, mooring systems, and reliability analysis. The Qiongzhou Strait remains one of the most studied crossing sites in the world. A submerged floating tunnel has been proposed there as a potentially superior alternative to both a bridge and a traditional bored tunnel. Analysis has shown it would be shorter, cheaper, less disruptive to shipping, and more resilient to the typhoons and seismic activity that make the strait so dangerous for conventional structures. China has also been pushing the boundaries of underwater construction in ways that demonstrate its readiness for the next step. In June 2025, the Jinan-Huanggang Road Yellow River Crossing Tunnel completed excavation of its underwater section. At 5,755 meters long and excavated by a tunnel boring machine 17.5 meters in diameter, it is the largest underwater shield tunnel currently under construction in the world. In 2024, the Dalian Bay Undersea Tunnel won Global Project of the Year. And a high-speed rail tunnel beneath the Yangtze River recently set a new record for the fastest underwater rail crossing ever built, with trains designed to travel at 350 kilometers per hour through a tunnel drilled to millimeter-level precision 89 meters below the river. Meanwhile, Norway has been studying submerged floating tunnels as part of its $40 billion E39 coastal highway upgrade. The Norwegian Public Roads Administration has explored floating tunnels at 4 different fjord crossings, including the Sognefjord. The concept there would involve a concrete tube about 30 meters below the surface, held in place by pontoons or tethers, allowing ships to pass freely above while traffic flows through the tubes below. If Norway builds one, it would be the world's first. But China has the engineering capacity, the government backing, the research pipeline, and the specific crossing needs that make it the most likely place for the first submerged floating tunnel to actually get built. The challenges that remain: it would be dishonest to pretend this technology is ready to deploy tomorrow. It is not. No submerged floating tunnel has ever been built anywhere. Moving from a validated computer simulation to a real structure in real ocean conditions is a massive step that involves challenges the paper itself acknowledges. Long-term corrosion in seawater is a serious concern for any marine structure, and a tunnel that has to last 100 years while constantly submerged will need advanced anti-corrosion systems. The connections between tube sections, where the structure meets the shore, and the behavior of the mooring cables under decades of wave loading all need further testing. Construction underwater, assembling and connecting massive prefabricated sections in open ocean conditions is orders of magnitude harder than working on land. The team's simulations are based on material cost comparisons that do not yet include fabrication complexity, underwater assembly logistics, or the cost of specialized construction vessels. Those real-world factors will increase the final price tag significantly. And there is an inherent psychological barrier. Every bridge and tunnel in operation today has precedent. Engineers can point to existing structures and say this works because we have built it before. A floating tunnel has no precedent. The first one will carry the weight of proving the entire concept to the world. That makes approval processes slower, insurance more expensive, and decision-makers more cautious. But here is what has changed. For the first time in the history of this concept, there is a peer-reviewed, numerically validated design that solves the 3 biggest problems: lateral displacement, fatigue life, and fire resistance, simultaneously at a cost competitive with existing solutions. The Tsinghua team did not just say it could work. They showed the math, they published the data, and they invited the entire engineering world to check their work. No bioplastic, no composite material, no single invention changes the world by itself. It takes the right problem, the right solution, and the right moment. Underwater tunnels have given us incredible things, but they have limits. And those limits have left some of the most important crossings on Earth unbuilt. A tunnel that floats does not ask the ocean floor for permission. It does not care how deep the water is. It does not need a mountain of bedrock to anchor itself inside. It just needs the water it sits in and the cables that hold it steady. If the answer to crossing the deepest waters on the planet was floating right there inside the water itself, what other impossible problems in engineering already have solutions hiding in plain sight, just waiting for someone to look at the problem from a completely different angle? If this video changed how you think about the tunnels and bridges you cross without ever wondering how they got there, give it a like and subscribe for more. Turn on notifications so you never miss the next one. There are related videos on the screen right now if you want to keep watching. Let me know in the comments which crossing you think should be the first to get a floating tunnel.